All right. Welcome to session 2 of AI Research School. Today we have our Intro to AI lesson given by Dr. Najib Khan. I'll give a quick bio of him before jumping in. Dr. Najib Khan is a founder and CEO of Serena AI. Which specializes in spatial temporal time series forecasting. Formerly, he was the lead data scientist at Global Relay. He contributed to voice transcription and NLP solutions. Additionally, Dr. Khan served as an adjunct professor at the University of British Columbia, focusing on reinforcement learning. So without further ado, I'll hand it over to Dr. Khan.
Thank you. Thanks everyone for joining this evening. So I'm sharing my screen, and today we are going to look into Introduction to Machine Learning. We are going to go through a notebook, and you have the link to it, so you don't need to record anything, or there are portions of this presentation where I will be coding, so you don't need to worry because you already have the solution. But keep an eye on when I am coding. If there are mistakes, then make sure that you catch them. So without further ado, let's dive in. So here is the outline. First, we will define machine learning in general, and then some main components of machine learning, for example, the models, the objective functions, and the learning algorithm. And then we will look at some examples of actually coding machine learning problems. So in the meantime, if you have any questions, make sure to join in, to put it in the chat, and then I'll once in a while sort of look at the questions and answer them. So let's get started. So what is machine learning? So machine learning is the study of algorithms that rely on a collection of examples of some phenomena. So rather than hard coding or writing logic, for example, if-else statements to perform a task, you have machine learning algorithms which learns from examples of some phenomena. And as you provide it with more and more examples, the performance of that algorithm improves. So that's the very broad sort of definition of machine learning. Now, there are a few types of machine learning, and there are types and kinds, and the field is growing really fast. So the taxonomy of machine learning is sort of expanding, but here we will keep things to the introductory level. So we will look at a few types of, a few very common types of machine learning problems or types. And the first one is supervised learning. So in supervised learning, what you have is a set of data points. So here we have x1 and y1, and then x2 and y2. So think of the x as the input and the y as the expected output. So this could be images. So we have an image 1, which would be sort of, let's say, an X-ray, and a label saying whether this tumor in this X-ray is benign or malignant. So this is sort of the supervised learning setting where you have the input data, and for each input you have the targets as well, the labels. And then the purpose of the machine learning algorithm is to, given this input data and the targets for a few examples, let's say 2000 examples, it can learn from this data, and for the examples that it haven't seen, so a new X-ray image, it can predict the label for that image. So that's the supervised learning setting. Now we have the next type of machine learning is semi-supervised learning. So in semi-supervised learning, we have a bunch of data that's labeled. So think of this as X-ray images, same as before, with labels for each image. But these labels were sort of provided by radiologists or really experts in a certain domain. But since this requires this labeling is an expensive process. So we cannot label all the images that we have. So we have some images which doesn't include the labels. So algorithms that can take advantage of these unlabeled data as well, those are termed as semi-supervised learning algorithms. In general, the number of labeled samples is much smaller than the number of unlabeled samples. So if some algorithm can take advantage of these unlabeled data, it's quite a lot of data. So those algorithms usually outperform algorithms that are trained only with supervised learning. So that's semi-supervised learning. The third type of common learning is self-supervised learning. So in this case, we have only unlabeled data, so inputs x1 to xn, but the labels could be extracted from the data itself. So and when we think of self-supervised learning, the goal is to learn a good representation or a good set of feature vectors from this data. So if you have, let's say, a bunch of images, what you can do is provide two similar images to the algorithm and let it predict whether it's the same image, or provide two separate images and let it predict whether they are different. So in this case, at least the algorithm will learn how to differentiate between two similar images, or sort of figure out whether two images provided to it are the same or different. And this helps the algorithm to distinguish between not only the inputs, but also come up with good representation of the inputs. So that's self-supervised learning. This is sort of the emerging area. And then the final one, which is very common, is unsupervised learning. So in this case, the goal is not to learn features, but to group data or find groupings of data. So you have a bunch of samples, x1 to xn, and you don't know anything about the distribution or the groupings in this data, and you want to find patrons in the data. So when this is the case, then unsupervised learning is what you go for. So those are some of the common terminology that you will come across, and in the next lectures, modules, you will learn more about each one individually. There are other more advanced forms of learning as well: reinforcement learning, active learning, transfer learning, continual learning. And there are a bunch of other sort of areas of machine learning that are out there. I put a few keywords here so that if you come across any of those, you're familiar with at least the words. More recently, so what we describe here, all of these, the ones that we described in the previous slides, this requires a whole lot of examples to come up with a good model or system to do the predictions. More recently, prompting is emerging as a learning technique, and what happens in prompting is, one of the techniques of prompting is few shot learning. So in few shot learning, you have a system built in where you provide a few examples to the system or the model or the algorithm, and it can predict from just a few examples, it can predict the next output for a given input. So here, if you provide misspelled words or misspelled animal names, then it is able to sort of predict the next input for you. So that's those are some of the main sort of areas of machine learning. Now, what are the common tasks that these learning paradigms could solve? So there are a few, and we will go through them in turn. So first, let's look at supervised learning problems or tasks. So the first one is classification. So we already saw, like in the previous slides, if you have images and a label, a target for each of the image, then you can say whether the for a given image, if the target values are finite. So in this case, it's just two values. The target is either benign or malignant. So if you have a finite number of outputs, then you model the problem as a classification task. If you have, let's say, some continuous variable, then in that case, you can't apply classification or can't model it as a classification problem. So when you have a finite number of output values or a categorical variable, then in that case, your problem is a classification problem. Okay, so what happens when you have to predict a quantity, for example, like temperature, or given an image, predicting their body temperature, or given some other measurements, let's say given a photo, predicting how many people are in the picture, like at an airport or something. So those kind of things are continuous. There could be hundreds and hundreds of values of that this target variable could take, right? Sometimes the output variable is continuous. So for example, in this case, if you were to predict, I don't know, like even temperature is a continuous variable. It could be 38.1 or 38.2 or 39.3 Celsius. So when you have continuous variables as the target, then in that case, you model the problem as a regression problem. Um, Recognition or detection is another thing. So we already saw the image classification, where you classify the whole image as containing a laptop or not containing a laptop. But detection is slightly different, where like you have an image and you detect uh, whether it contains a given object or not, and at which location does it contain the the, the object. And this is sort of like classification plus regression, because you need to specify where the bounding boxes are. So similar sort of classification and regression could be combined in various ways to come up with, to model a variety of tasks. Segmentation is another one, where let's say you are given an input image, and you come up with segments of semantically similar objects inside that image. So if you think of it, an image is made up of pixels, and you are basically classifying each pixel as corresponding to a given object or not. So classification could be seen as in this case, as a segmentation task. Finally, in supervised learning, time series forecasting is another problem, where you are given the past history of a given variable, and you want to predict what would be the next value of that variable. So that's again modeled as a supervised machine learning problem. Now, the next one, and this falls into the category of unsupervised learning, is clustering. So you're given some data points here, and the idea is to, given these data points, come up with groupings of these data points. And here, the groupings are sort of shown in terms of colors. So each color represents a single group. And so if you have a higher dimensional sort of data, then in that case, you wouldn't be able to visually see it. But with clustering algorithms, you can find out, given given all the data, how many groups are there, or given the data and a new data point, what is the closest grouping to this data point. So this is again useful in many applications. So so far we have just looked into the basics of like what machine learning is, what are the types of it, and what tasks can be solved with machine learning. Are there, before moving on, are there any questions we can pick up so far? Can someone look at the, are there any questions?
I think Angelina has a question. I think you can feel free to unmute your mic and ask it.
Okay. Sorry, can you go back to a slide with a COVID example from Italy?
Sorry, from which
There
one?
was like a graph and there was example.
Sorry. Time forecasting one.
Yeah, this one. I have actually a question. Is time series forecasting is always correct? Or
So none of the machine learning algorithms are sort of deterministic, so they are probabilistically correct, and there are certain assumptions that they are based on. So one is the data distribution of the training and the testing has to be similar. So if that's the underlying assumption of machine learning algorithms. So there is no guarantee of a given instance being correct. Like at a given point, would this be exactly the next data point would be like this? But in expectation, the algorithms are correct. Yeah. So.
but what kind of data are we using, for example, for this one? So is it like a real-time data which changes like every time, so we can kind of like have an accurate graph? Like what kind of data do we usually like use for this one?
Yeah, so in this case, when we say time series forecasting, so in time series, we only take care of like the previous data sample. So by definition, given, let's say, yt at time t, we are predicting, given this yt and other yt minus 1, yt minus 2, we are predicting yt plus 1, right? And so here the assumption is that yt plus 1 would follow a similar distribution. So this would be distributed according to some distribution d, and that would be very similar to how yt minus 1 and yt minus 2 are distributed. So if the distribution changes, then it wouldn't be accurate. But if the distribution of the data is the same, then in expectation, yt plus 1 would be correct.
What is the percentage of, for example, of an error which we could have potentially, like in time series forecasting? Like, is it 5-10%, or like how do we like usually also define it?
Yeah, so as I say, like it's if these assumptions are correct, like 100%, then your model will output 100% of the correct.
Okay, so everything is based on the previous like a time series.
Yeah.
Oh, okay,
and since this is an approximation, so your output is also an approximation. So you can't generically say like, okay, every time series forecasting is going to be 10% accurate.
Okay, thank you.
No problem. All right, anything else? If not, then we can move on to the next section. Okay, so now let's move on to, we described from the outside what machine learning is, what are the types of machine learning, and what tasks we can solve with machine learning. But what does a machine learning system look like? So here are the three components that you really sort of need to know about when dealing with machine learning. So the first one is the model. And the second one is objective function, and the third one is the learning algorithm. So we will look into a few models and also the objective function and the learning algorithms. But let's look at the overall picture here. So you have a class of models. So here I've define it as a box here. And then the learning algorithm picks one of the model, like it's a class of models, and you pick one out of the many models available to you in that class. And then you evaluate it, saying like, okay, how good is this? But how would we know whether what we picked is good or not? So that's where the objective function comes into play. So this objective function basically takes in our data set, and it tells the learning algorithm how good this model that you picked is. And so the learning algorithm decides, oh, this is not very good. So it puts it back and picks another one, or like slightly changes it. And then it continues this process, and eventually once it gets tired or it finds a really good model, then it spits that model out, and that's the output of the machine learning system. And so once we have this best model, then we can use this to make predictions for new data. So that's the higher level sort of overview. Let's now look at what the models, the objective functions, and the learning algorithms look like. So models, a model basically what it is, it relates inputs to the output. So the most basic model is basically linear regression. So you have the inputs, and the inputs are represented by a vector, and the vector contains components. So here we have x1, we have, x1, x2 up to xn. So these are the inputs, and these are multiplied by these weights, w1, w2 up to wn, and we get the output. So that's our linear regression model. So given any input and the weights, we can compute the output. So that's the linear regression model, pretty simple. Here, how we compute the output. So let's say our weights are all equal, and if they are equal to 0.25, 0.25, 0.25, and 0.25. And then given an input, let's say 2145, we just multiply the two and add them together to get the output y. So this is what's happening here. Hopefully it's clear for everyone. It's pretty simple. So here is our coding exercise, and the idea is to given this linear regression model, we need to implement this in Python. So I will try to think about it a little bit. I will try to do it as well, but let's do it together. So how would you implement it? So here is a function, a Python function, linear regression model. We have inputs x and weights, and now we need to calculate the output. So to do that, think about it, what we need to do. We somehow need to find out what is the length of the inputs, right? So let's say n is equal to the length of the input, right? And then for each input, what we need to do is we need to multiply the input, the ith input with the ith weight, right? And what we need to do with this, we need to combine all of these into the output. So you'll say output plus equal to, let's say, make it really simple, output equals output plus the input xi times the weights of I. So this is our basic linear regression model. Hopefully everyone understands what is happening here. It's really similar to what we have on this slide. We are just implementing this line. So that's our linear regression model. We could have equivalently looked at the length of the weights, and it would be the same thing because inputs and weights have the same size. Okay, so that was the model. In the previous case, we looked at linear regression. That's the first model. What if our output variable is not a continuous value, but rather it has discrete values like two classes? So in that case, we can use what is known as logistic regression model. And the logistic regression is very much similar to the linear regression. So you have the same W times X, so that's the same thing, but you pass it through another function called sigmoid. And this basically gives you the output for the logistic regression. And what is this sigmoid? It's equal to 1 divided by 1 plus exponent of the negative of the input. So it looks like this. And the property, there are some interesting properties of this function. And one is that it is a probability function. So its value is between 0 and 1. And when you integrate it, it also integrates to 1. So that was the, we looked at linear regression. We implemented linear regression model. We looked at logistic regression, and we could implement it if need be. Maybe it's a homework assignment for you to do that. And then let's look at another model known as decision tree. So what is happening in a decision tree is the output is equal to a sum of the branches of that tree. So here is one tree. So let's say you have some inputs like x1, x2, and here instead of x1, I'm calling them A and B. So these are your inputs. And if your inputs value is less than, let's say, some threshold T1, then you take this branch. And if it is greater, then you take this other branch. And let's say you took this first branch, and then your second dimension, x2, is less than some threshold, then your output is 0. And if it is greater, then your output is 1, and so on. So you could think of this as if-else statements in normal programming. But the only difference between this and a hard-coded program is that the questions that you are asking, should you ask A less than T1 first, or should you ask B less than T2 first? So the machine learning algorithm will pick this for you automatically. So that's where the machine learning comes into play. And then the other thing that it learns is this T1 and T2. So these thresholds, these are learned automatically. So this is a very toy example, but imagine you have hundreds and hundreds of inputs, like age and a lot of like health data and all other sort of inputs about a person. You want to predict whether they are healthy or not healthy. So so there could be a whole bunch of questions that or like questions or inputs that you could record from an individual. But how do you sort of structure that, and what are the thresholds for your output? Those could be learned automatically. So that's a decision tree. We wouldn't go into the detail of support vector machines, but you will hear them when you work with machine learning that support vector machines were also used to be very popular, and not these days much. I'll skip over these. And the final one that we will look into is the neural network. So these are very popular, and probably you will hear a lot more about these in the future. So the neural networks are very similar to logistic regression and linear regression. So if you look at this part, this is very much like linear regression. So you have, let me just spell this out. So you have, before you had linear regression is similar to this, W time X on the previous slide. So that's this part. And then when we applied sigmoid to it, so it became the logistic regression. So it's like this. So it's this part. And now you do the same thing over and over again. So here at the next level, we have this linear regression applied to this part. So that's like one layer of the network, and this is another layer of the network, and a sigmoid is applied to it again. And then you can have this input to the next layer and so on. So that's what a neural network is. So each one of these is basically a logistic regression of the previous input. So this is a logistic regression of the inputs from the previous layer. So these are just representations or models that you sort of need to be familiar with. Now let's look at what these which one would you sort of use, right? Like, is linear regression good, or logistic regression, or neural network, or SVM, or decision tree, right? So a lot of it comes from experience, but also there are some general guidelines. So model capacity is one of the deciding factor. So if you have some inputs and targets, you need to sort of, based on the inputs and targets, you need to decide on what model do you want to pick. So if the mapping between inputs and outputs is a linear one, then you want to look into linear regression. And so each model that we described previously in the previous slides have a certain capacity or a certain representation power that it can use to describe the mappings from input to output. So let's look into each one of these. So in logistic regression, we have a straight linear boundary between the two classes. So if you are doing some sort of classification, and if you see that, okay, your models could be separated into, your data could be separated into two classes using a linear boundary, then you can use logistic regression. But if the boundary is more complex, like somewhat sort of like not very clearly separated, then you can use these other models, for example, decision trees that we looked into, or SVM, or a neural network. And among all these, I think the neural networks are the most popular ones, and they are the most flexible ones because they can approximate arbitrary precision boundaries between classes. So that's a little bit about the models that you need to be familiar with. We looked into linear regression and implemented it, and we looked at a few others as well. Any questions so far before I move on to the objective function?
We do have a few questions in the chat. I'm gonna read them out. The first question was, in general, what's a model, or what is it modeling?
Yeah. So what is a model? It's basically when you are doing so what it goes back to machine learning in general, right? What is the purpose of a machine learning system? So you have some inputs X, and here is the model. So the input goes into the model, and it predicts some output for you. So you can write some sort of like Python code or logic to produce, given a certain input, give me an output, right? But in machine learning, we need to sort of come up with a program or code that, given a certain input, it predicts the output without hard coding all the values inside this model. Now, linear regression, as we implement it, is a model that maps, given inputs x, it maps to output y's. So hopefully that's sort of a simple explanation of a model being something that, given some inputs, it maps those inputs to the outputs.
All right, thank you. The next question is, in terms of set functions and set relations, what is the difference between a model and a relation, or otherly worded, the difference between a function and a model?
Yeah. So think of the model is exactly as a function. Just think of the model is a parametric function. So basically, if you say linear regression model, you could just give me a second. Okay. Yeah. So if you are looking at let's say a linear regression model, just think of it as a function. Given x, it produces the output y. But this function is parameterized by the weights w. So these w's are the parameters of this function.
Okay, thank you. The next question is, were wait, sorry, I think that one's answered. How are the thresholds determined? I think that was for the sigmoid. I'm not sure.
Probably the decision trees. Yeah. So
Okay, yeah.
So yes, so that's the next part, right? The learning algorithm basically determines what would be the thresholds, and also whether you should ask the question about the B first or the A first. So it's the same thing in linear regression. So this was for decision trees, for logistic regression, and for linear regression. The same question you could ask here is, how are these W's determined? Because these needs to be determined through a learning process, right? So we will look into it in the next sections as we sort of move towards, where is it? Yeah, here. So we looked at the model, and the model has some, you can think of the model as the function with some parameters like the thresholds or the weights. And now how do we find out those weights or thresholds? So that would be the learning algorithm that does that. But before that, we need to look into objective function. Are
Okay,
there any other?
There's, I think, about three more questions. Are you all right with more questions, or should we move on? Or okay, more questions. Okay. So next question is, do we use backtracking in decision tree induction?
Yeah, backtracking. You could use backtracking, but there are other sort of, so like backtracking kind of algorithms are useful when you are purely working with discrete quantities and discrete things and discrete values. But what if you have continuous values, right? So or continuous variables. So in that case, the backtracking algorithms might not be the most suitable ones. But in the discrete case, there could be potential uses of backtracking. Yeah, but the learning algorithm in machine learning in general, you use this framework where you have a class of models. So decision trees would be a class of models, and then the learning algorithm picks some thresholds and asks the objective function, is this threshold good or not? And then the objective function provide some feedback to the learning algorithm, and it iterates over its models and produces the best model that it could.
Thank you. The next question is, what does hidden mean in neural networks diagram?
Yeah, so in neural networks, hidden means, so here the inputs are sort of x1, x2, x3, so that's given to you, or like we already know what they are. And the outputs are also observed, so y1, let's say, and y2, so these are observed, but there could be many layers in between the inputs and the outputs, and the general terminology of these are that this is a hidden layer, that is, it is not observed in the data. So you have only the inputs and the outputs, but everything in between are sort of layers that are hidden from us, or we don't observe its values in the real world.
Okay, thank you. The last question is, what's the difference between the definition of a linear regression and a linear transformation?
Sorry, what is linear
Oh,
time? Could you?
Yes. What is the difference between the definition of a linear regression and a linear transformation?
Yeah, so it's very similar terminology, a function, a mapping, a model, and linear regression versus a linear transformation. So a linear regression is basically a linear transformation of the input, and so you could think of them as like very similar. Sometimes the bias term is used to differentiate that, okay, it's a linear transformation plus a bias term. That is it may not be sort of obvious to what I'm talking about here, so let me go back. So here you have a linear transformation here, or linear transformation here, plus a bias term. So they're very similar things.
Okay, thank you. Oh, and a follow-up to that is asking, it's an affine transformation.
Yeah, that's
Okay.
correct.
All right, thank you. I think that's all the questions, and we're good to move on.
All right. Okay. So we looked at a bunch of model classes, and now the question is, given a model class, let's say linear regression, we set the W's to certain values, let's say 0.25, 0.25, as we saw in the previous sort of animation. Then how does how good is that model given our data set? And that's the function of the objective function to evaluate a given model. So as I described, objective function is used by the learning algorithm to evaluate different models. So it's just like the model was a function of the input and the parameters. The objective function is also a function, but it's a function of the data set and the model that we have. So a little bit of terminology or symbols. So let's assume that we represent our model by a variable h. So that's our sort of function h in a class of models. So this could be all linear regression models, or all linear transformations, or all decision trees that are possible. And then we have a data set D, which is the data set that's given to us of inputs and target pairs. So you have a bunch of examples. We have n examples here that comprises, that makes up our data set. And then we have another function j, and it evaluates, given the ith example, we pass that ith example through our model. So that gives us the output of the model, and we have the desired output, which is yi in the data set. So this function j basically computes how good or how sort of close these two quantities are, because the basic idea is for these two to be very close, because if our model is good, then it should predict h of xi almost equal to yi, right? So this was for a single example, but we have not just a single example, but we have n examples here. So all we need to do is just sum this up over all the examples, or make summing would sort of depend on the number of examples. So let's take a mean of these quantities. So here we have the mean over the whole data set. So we have n examples. We figure out how good is the model performing on a given input, and then sum and divide by the n. So that's our sort of objective function over the data set and over the model. So now this is the general form, but now you might be thinking, okay, what is this j? Like, what kind of function we can use here? So you could use anything for closeness of the model output and the actual output. So you could, let's say you use the difference, but in that case, the difference will cause the model to be biased towards always sort of predicting lower, so that it can come up with a lower value. You could make this closeness, you can represent this closeness by the absolute difference, and that will work. You could represent this by the squared difference, and that would also work. In fact, that's the most common sort of objective function out there. So common objective functions are for linear regression is the mean squared error. So in that case, you would have this function represented as the squared error between the model output and the y. And in classification problems, you use cross entropy. So let's look at how we can represent mean squared error. So we are given an example, xi and yi, and then the model predicts, we have the model h, so we pass the xi through the model, and it predicts something yi hat. And then if we have a really good model, if h is good, then a good model will produce yi approximated close to yi, right? So this is the mean squared error. So we find the error between the actual output and the model's output. So that's our error. We square it. So error squared. And then we compute this for the whole data set. So for example, I plus 1, I plus 2, and so on. So for all the examples, we sum the squared error, and we divide it by n. So that's our mean squared error. So hopefully it's clear to most of you. If you have any questions, please go ahead and ask before I start to implement the mean squared error. Are there any questions?
There's a question regarding the objective function. So back on that page here, the formula going j and then having the parameters. So someone's asking, wouldn't j have to be a metric, or can we get away with using something weaker?
Yeah, so it's good to be a metric. So just for everyone else, what a metric, loosely speaking, is it should have some properties. So if you provide like two inputs that are similar, then it should equal to 0, because if x and x, they are the same thing, then the output should be 0. And if they are if they are commutative as well. So these are some mathematical properties of functions. But in general, in machine learning, most of the time it's useful to, or almost all the time, we use this J to be a metric. But in some cases, it doesn't need to be sort of the case, because machine learning algorithms in general deal with approximations. So if there is an objective function that really works well in practice, but it doesn't satisfy the mathematical properties, it's still used because in practice it has good performance. Yeah, so it doesn't necessarily need to be symmetric, at least, because I'm thinking of KL divergence. So since this is an introductory talk, so we don't need to sort of understand all of that. But KL divergence, even though it's a metric, but KL divergence between x and y is not necessarily equal to y and x, so it's not sort of symmetric. So, but it's still used in as an objective function. Okay, so are there any questions, or shall we move on?
I think you answered everything. Thank you.
Okay, so let's implement the mean squared error. Hopefully I can do this, but think with me. So we had, let me just write the formulas here. So on the previous slides, we had y minus y, this thing, and we squared it. And then we said it's like the ith one. So then we summed it over I from 0 to n minus 1. And then we divided by 1 over n. So let's type this in. So we have the first, let's find what is n. So n would be the length of the target or the input or the predicted. So that's our n. And then for each of the input, what we need to do is y target of I minus y predicted of I. So that's our error. Okay, and then we need error squared. So error equal to error times error. And we need to sum it or all the values. So let me just call this MSE equals 0. Or maybe like for everyone to be following, let's call it total sum or error sum. So we have error square sum equal to error plus error. And then, so we have the error sum, we just need to, or squared error. Okay, so we have the n, the number of input samples. We have the error sum, squared error sum equal to 0. We compute the error for each of the targets and the predictions. We squared it, so that's our squared error. And then our squared error sum is equal to our squared error sum plus squared error. And then given the squared error, we need to divide by n, and that is our mean squared error. Okay, so that's our mean squared error. Okay. Now, hopefully everyone follows what we have. So we have a model now, linear regression model that we defined previously, and we have the mean squared error objective function. So now we come to the part where we look at the learning algorithm. So here we defined, or at least became familiar with the model. So there could be linear regression, logistic regression, decision trees, neural networks. So those are your models. There are objective functions. Data sets, you already sort of know that it's a pair of input and targets. And then objective function, we looked at mean squared error here. But if you have other problems like classification, in that case, you use cross entropy or KL divergence or something like that. And then finally, we are looking at the learning algorithm. So given a class of models and an objective function and a data set, the learning algorithm basically decides which of the model is the best. So let's look at the learning algorithms. So the learning algorithm, given the objective function J, which is a function of the data set and the model parameters. So this W in here is the weights of a model that contains weights, but for a decision tree, these would be the thresholds or all the decisions that you can make within a decision tree. So those W will represent that. And then the idea of a learning algorithm is to minimize this objective function over the model parameters W and come up with the optimal model parameters. So here is how we will proceed with this. So we say we have n samples, which is in our data set, and we need to find the model with the lowest objective function. So in general, this goes back to the questions that were asked about the time series forecasting and whether we can guarantee that the model output would be the same or similar to the input or to the similar to the data set. So in general, you can't have any guarantee that if you do this optimization, find these optimal parameters, and find the optimal model, that it will produce correct result in general. But if you assume that what your data is here, if this is distributed according to some distribution D, and if you have a new x new that is also distributed according to D, then this model H will perform well on that x new. So in that case, your model's performance will be, there could be some guarantees mathematically that this would be close to the actual output y new. Okay, so coming back to the optimization part, we need to, in order to learn a good model, we need to do this optimization. And the most common way to do this is using what is known as gradient descent. And this could be used for not only for linear regression and logistic regression, but a whole lot of other model classes as well, including neural networks. So to briefly describe what gradient descent optimization algorithm is, consider this beautiful mountain, and consider this as the objective function in 2D or 3D. So let's say your target, or like the lowest point in the parameter space, is this. So this is where I want to sort of reach. But let's say you are in this position. So if your friend tells you that, okay, to reach here, we need to go this way. So clearly, they're not in their right mind. So you don't want to follow it. The most sensible thing is to do is to come down this way, right? And why this way? This is because this is the direction of the steepest descent. This is the direction where you are coming down or lower. So you will take steps in this direction until you reach some lower point, let's say here. And then once you are at this location, then you want to probably follow this direction, because this is the direction where the slope is maximum or coming downwards. And then eventually you will reach the lowest point here. So just following this simple procedure takes you from a very large value in the objective function to a minimum in the objective function. So how do we figure out, like, okay, which direction to go? In mathematics, if you remember, the slope of a function is represented by the derivative of that function. So we will use the derivative of a function, but that would point towards the ascent. So you want the negative of the derivative. So this is how the algorithm works. You start with some initial w, and it doesn't matter where you start. So just start with some random initial weights, since we don't know what the actual w's are, and then follow the direction of steepest descent. So given the w at time 0, at time 1, what you do is w at time 0 minus some small parameter, that's the step size or the learning rate, times the derivative of the objective function with respect to the weights. So that's your update equation. If you take many steps in the descent direction, you will eventually reach W, which will result in the minimum cost function or objective function. So this is the basic idea of the this gradient descent algorithm. Now, what is W? That's the learning rate. That's equivalent to the steps that you take here. So if you have a larger learning rate, then in that case, you will be taking very, very large steps. But if you use, so let's say, let me just visualize the steps here. So if you are coming from here, if you have a very small step, then you would be taking very small steps here, very slow learning rate. But if you have larger learning rate, then individual steps would be from time step t equal to 2 to time step t equal to 3, you will be taking a huge step. So as you can see, if you are taking too long, too large steps, then this could be problematic, at least in this area. So let's visualize that. So here, this steps or learning rate is visualized. So if you have appropriate sort of steps, then you will converge to the optimal solution. But if you are taking too large steps, then you will jump around the solution and you would never sort of settle on a given value. So a lot of the times when machine learning practitioners talk about, they say I'm doing hyperparameter optimization, and a lot of the work of machine learning practitioners is to just tune machine learning algorithms, and this is one of the most critical sort of parameter in machine learning models. That is the learning rate. So good to sort of be familiar and know what are the consequences of very small step size will result in very slow learning, and very large step size will result in divergence. Okay, so let's do another quick activity, and we have already looked at the model. So we have the linear regression model. We have already implemented the mean squared error as our cost function or objective function. And now we need to sort of compute this. So as we sign here, we need to find the optimal W, and that would be W minus the learning rate times this quantity. And that's called the gradient of J, or the gradient of the objective function. So let's compute this objective function. So here we have J, this is J, and then we need to compute its derivative with respect to W. So from high school math, you can see that we take this 2 out here. We have yi minus w times xi and 2 minus 1. So that's why we don't have a power to this. And then the derivative of this part, which is negative of xi. So this is our gradient of J formula. And the activity is to compute this quantity. So, so the first step to compute this, we have the inputs x, and we have the target y's, and we have the weights of the models. So the first step would be to compute for each of the input x, we need to compute the predicted y. So let's say we have m examples. So the length of the input is m. And now we need to do model predictions, or predicted y, basically. Predicted y is equal to, since we need to do it for many examples, so let's iterate over each of the inputs. So for I in range of m, now we need to do prediction for the for x of I. So we need to do a prediction, and we already defined a model previously, the linear regression model. And this model takes in the input, but it also requires the weights. So you'll pass in the weights. So that's our prediction. And then we add this prediction to our predicted y. So predicted y, append prediction. So this will give us x, y, and the predicted y. So all the ingredients are there. So now we need to compute the gradient. So gradient equals to 0. So let's go through all the inputs. So for I in range of m, we have if we look at the formula there, we have this formula, right? So this is the predicted y minus the actual y times xi. So let me put this in. So we have the predicted y of I minus the actual y, right? And we need to multiply this with x of I. So that's our gradient for this particular example, and we need to add this together for all the examples. So let's say gradient equal to gradient plus value. Okay, so that's our gradient. So now we have almost all the ingredients to do to do the learning. So we have the gradients, we have the weights, we have the model. So let's compute or implement the stochastic gradient descent algorithm. Excuse me. So we have the gradient equal to the function that we just defined. So what we need to pass to this compute gradient method, we have the train x. So we pass that in, we pass the train y, and we need to pass the weights. So this will give us the gradient, and then the formula for the weight update is weights are equal to, the new weights are equal to the previous weights minus the learning rate, which is given to us, times the gradient. And this will give us the new weights. Okay, so this is the gradient descent algorithm. Okay, so now we have all the ingredients for the linear regression model, and now it's time to basically use it to do some predictions. So we will be applying it to a real world example, not a real world, but a toy example, which is to predict diabetes progression. So we have a data set of 442 diabetes patients, and our X is a few variables collected from the patients. So, for example, their age, gender, BMI, blood pressure, and some blood measurements as well. And our Y is the percentage of progression of diabetes, so 1 year after the measurement. So basically you are predicting, if this model becomes successful, then bring any person to the lab, take some measurements, and predict whether they will have whether their diabetes would be cured 1 year later or not, or worsen, so that you can do some intervention. So a lot of the times in machine learning, you need to do a lot of pre-processing. This is a toy data set, so I have already sort of pre-processed the data, and you have nice sort of data set available to you. So let's just go through the code to see how we can apply the linear regression model that we just coded in this lecture to do this prediction. So we get the database here. So we have the train X and the train Y. We set the D, which is the length of the input, or the size of the input features. And we initialize the weights with some random values. So since in linear regression, we need D weights for D features. So there are the weights, we append a random value to the weights D times. So at this point, we will have weights equal to the size of D. And now for 5,000 times, we perform the gradient descent algorithm, and we constantly provide the train X, the train Y, and the weights, and set the new weights to the gradient descent weights. So let me run this. Okay, so I have to run the previous cell. Let me run this. So it's running the gradient descent algorithm, and it encountered some numerical errors in between, but eventually it did complete. And now let's do a prediction for, let's say, train X of 9. So the 9th example, given the weights of the model, what is the prediction of this model versus what is the actual value? So since we coded it ourselves, it may not be that great. Okay, so let's analyze what we have here. Compute gradient. Linear regression is okay. Everyone, help me figure out if there is any error in the code. So we have linear regression. We specify n. We have the output set to 0. I in range of n. That's correct. Output is equal to output plus input x times weight. So this seems correct. Okay, so let's run it here. Linear regression model. Let's say 1, 2, 3, 4, and let's provide some weights. 0.25. Okay, so this should compute the average of 1, 2, 3, 4. So that seems to be correct. Let's look at our second code. Okay, mean squared error. We have the target. We have the sum squared error sum error y target minus y predicted. That's correct. Squared error is correct. We sum it together. Okay. Okay, so looks good. Okay, compute gradient. M is the length of y, x, predicted y. I is range m. We do the prediction using the linear regression model given xi and the weights. And we append it to the predicted y. And then for each of the input, we have the gradient equal to gradient predicted y minus so this seems to be correct. And then gradient compute gradient. So we are computing gradient, train x, train y, and the weights. And turn the weights. Okay. So where is, let me analyze the train length of train x. Okay. Okay, somewhere. is it here? So we have predicted y equal to linear regression model output. So we have xi as the input appended here. We have the gradient 0, gradient equal to gradient plus did y minus yi times x of I. And then, so if you look at, so here so this is the formula we are implementing. So it seems like we missed some part. So here, as you can see, we have this, right? So here, where is that thing? So it's missing. We are just summing it up, right? But we are not applying this part, right? So we need to do that, fix this. So how do we do that? We'll have to multiply gradient by 2 divided by m times gradient. So this gives you the same formula. So 2 divided by m, and then the summation is there. So here. So this was the missing piece in our code. This gives you sort of a little preview of like, okay, when your thing doesn't work, like how do you sort of go through and figure out what went wrong. Hopefully some of you have been sort of chasing the same way I was doing it and trying to sort of figure out like if you can find it quicker than me. So, okay, let's see if it works this time. Okay, so no errors so far. And now we see that our model predicts 160% progression versus the actual is 310. So not exactly accurate, but at least it's on the same side. Like, okay, you need to worry about your diabetes progression. Let's try another example. Let's say 90. What is the model prediction? Yeah, so the model predicts that, okay, your diabetes will get worsened 1 year from now by 16%, but the actual is actually only 98%, so not that bad, or not great, but like it's something that we just coded in one lecture. So that's the okay. So this gives you a sort of a high level overview of how you can use or what happens under the hood of the machine learning model. Of course, you wouldn't be coding all of these by hand or like just the way we did it today. There are very good libraries out there that could be used to do this sort of work. But I wanted you to experience what is under the hood. So I'm going to move to the next section, but if there are questions, I would be happy to pick up a few of them. Are there any sort of burning questions that we can look into?
There are a few questions. Thank you for going through the collaborative exercise. Some people were typing in the chat what they were thinking, and some of them were asking if we needed an activation function here. And if you could explain what an activation function is and why we didn't use it here, that would be nice.
Cool. Yeah. So as we started here with the model, so let's go to the very beginning. Yeah. Okay. So here we started with this slide where we looked into the different models, and so we decided that we are going to implement linear regression. So in linear regression, there is sort of no activation function. So we will look into what what an activation function is. But we decided to implement the linear regression, so we did that. And here we decided to go with mean squared error objective function, so we implemented that. And then in here we went with the stochastic gradient descent algorithm. So any machine learning sort of algorithm or system that you come across, you would have similar choices to make. Here we coded them by ourselves, but in majority of cases, you would say, okay, I'm going to use a decision tree. So you would just specify that, okay, I need to use decision tree. You would say, okay, I need to use mean squared error loss function or cross entropy loss function. You would just specify that, okay, I want to use that. And similarly for the learning algorithm, you would just specify, and these are all implemented for you, so you wouldn't have to worry about those. As far as the question related to an activation function, that's mostly used in neural networks, and this sigmoid function that we looked at, this is basically an activation function. So in our case, our problem was a regression problem. That is the y that we were predicting was like continuous value, let's say 112.325, so something like that. So that's why we didn't have to use this sigmoid function or activation function. But if we were to predict whether the diabetes progression would be 100% or more or 100% and less. So in that case, we could say, okay, apply an activation function, and then its value could be either 0, the output value could be either 0 or 1, and 0 corresponding to like less than 100 and 1 corresponding to greater than 100. So that would be a classification problem then. So since we were doing a regression problem, we didn't have to use the activation function or the sigmoid function.
Okay, thank you. We have another question regarding if we choose a different regression model, will we need to recalculate and recode our gradient descent algorithm?
Yes. So if you choose, let's say a different, let's say a decision tree regressor or a support vector regressor or some other neural network regressor, then in that case you would have to redo your computations and compute the weights for the new model. And also the code that we wrote for the stochastic gradient descent, they would more or less stay the same, because as long as your parameters are sort of stored in a vector, the learning algorithm will work, because it doesn't know anything about your model per se. It just works with the weights and changes these weights.
Okay, thank you. There is another question. Is there a way we can look at models analytically and prove how fast a model converges, or if it converges at all without just writing code and running it on a lot of data?
Yes, so the linear regression model and the logistic regression models, these are linear, so there are theoretical convergent proofs for convergence of these models. But when you look into neural networks, those are nonlinear models. So for nonlinear models, it's much harder to do a theoretical analysis of the convergence. But the ultimate goal of machine learning is to do something practical, right? So you could, in theory, prove that your linear regression model converges, but proof is of no use if it is not like usable in the practical scenario, where like, okay, you made a few assumptions like linearity assumption in your analysis, but in real life that linearity assumption doesn't hold. So given the linearity assumption, your proof is correct, but it's not going to work in or translate to the real world. So that's why mathematics and proofs are not as useful for applications, but they are very useful for coming up with new machine learning methods and new machine learning algorithms.
Okay, thank you. Someone's also asking if we could run into challenges with different types. They're saying that the get diabetes data function is returning numpy arrays, but the other functions are returning Python lists.
Sorry, I didn't get the question. Like,
Oh yes, they're asking if uh, there would be challenges with different types, if that would be an issue, because one of them is numpy arrays, while the other functions are Python lists.
yeah. This was a toy implementation. So certainly, if you were sort of working with um, real problems, then NumPy array is the way to go because those are optimized for computations. Here, I was just implementing a very basic sort of um, problem. So I wanted to keep it really simple, and that's why I just used lists and really spelled out the code as much as I could. But in general, you would always want to use NumPy arrays for ML.
Okay, thank you. We have, I think, one more question, and asking in your definition of SGD, you took the partial derivative of J with respect to W. But what is W? They understand that it's supposed to represent the weight, but what happens if we have multiple weights? Where does W live essentially?
Yeah, that's a good question. So W here, that's why if it was just a scalar, we would call it just a derivative of the cost function or the J with respect to a single scalar. But in this case, it's a partial derivative of J with respect to W. So W is a vector in this case. And when we define gradient, that's gradient of a scalar function with respect to a vector. So what we would have here, let me just spell it out here. So we have W. We have W. So there would be like W1, W2, up to WD. And so when we pass it through this gradient gradient of J with respect to W, then it will give us another vector, which would be partial derivative of J with respect to W1, up so on, partial derivative of J with respect to WD. So this is how it looks.
Thank you. I think that answers the question. I think there was a follow-up in regards to the question on if we could find something like another way of finding how a model converges. So if they're asking if we can't prove if something converges, we can't be comfortable using it in practice because we don't know how close enough it really could be. So they're asking why we use it, I assume.
Yeah, so convergence proofs are one thing, and then using them in practice is slightly different, right? So um, even though you can't prove something mathematically, you can still do very thorough um, experimental empirical work to prove that the model works. So we will look into it in the coming slides. Like I have a few slides. We need to when we are sort of using a model in real life, we need to test it on a test data set and really make sure that it produces reasonable outputs on the test data. And so until we do that, we cannot use it in real life. So the alternative to proofs in machine learning or in empirical work is to empirically sort of first satisfy ourselves that, okay, on a test data set that's not been seen by the model previously, it performs reasonably well. And once that's the case, then we need to use it in practice.
Okay, thank you. I think that answers all of the questions. If I'm missing any, you can feel free to raise your hand and ask. But yeah, thank you so much.
All right, great questions. Okay, so I'm assuming everyone is familiar with plotting, but if you are not, we are looking at a few plots. So in Python, you could just define two lists and do a plt.plot, and it will plot the data for you. So okay, so that was a little bit of a digression, but let's look at some libraries for machine learning. So in the previous slides, we went under the hood and looked at the linear regression model, implemented it, MSE, gradient descent, all of that. You don't need to do this again and again. You can use um, a library called scikit-learn. There are a lot of other libraries as well these days, and those libraries specifically scikit-learn helps you to just define one liner of code, and it will set you up for set up the model and the learning and everything for you in one line of code. Of course, now that you have implemented some of it, you would be better in a position where you can say, okay, yeah, I know what is happening under the hood of this function because we have implemented one of it. Okay, so let's do some more exciting work here on a slightly complicated data set, and we will do the handwritten digit recognition with this library scikit-learn. So the scikit-learn library contains a module called datasets, and you could use that to load different datasets. So here I'm loading the digits datasets. It contains like X is the inputs and Y is the output. And let's print the length of the inputs. So that there are about 1700 examples, and let's see one of them. So it's very low resolution, but you could probably guess that it's a 3 here. Okay, so this is a logistic regression, or like this is a classification problem because we have plotted the input here, but let's see what the target looks like. So this was input 13, so let's look at the target 13. But target 13 is a 3, so it seems like the data set contains digits and their labels. So labels are from 0 to 9, so that indicates to us that we can implement this as a classification problem. So we don't need to do a whole lot of coding. We can just import the logistic regression model from the scikit-learn library, and we can provide it with the inputs and the targets. So this is the fit method on that logistic regression model. We say fit this this model to this data, and then let's pick an index, let's say 100, and let's predict for the 100th input. Let's see what the model predicts. So let me just run this. It will take a few seconds to train. And here is the plotted image of this 100 input, so which is a 4, and the model prediction is also a 4. So within a few seconds, you are able to run this model, or like train this model. Let's pick another example. Let's say 300, and I don't want to train it again, so let me comment this out. It's a 6, 7, yeah, and the model predicts a 7. Let's say 310. Yeah, so it seems like on the training data, it's really good. Okay, so now the question comes like, okay, we don't have any theoretical guarantees, and how do we know that that what we trained is good enough? So there are a few metrics that we can look at. So the first one is the accuracy. So given the model outputs, how much were the correct outputs of all the outputs that were presented to the model? So that's accuracy. So you could compare the accuracy of the predictions Y prediction and the actual Y using scikit-learn. So here we see that the accuracy is 1 or basically 100%. So it doesn't seem right because a machine learning model cannot be 100% correct. It's too good to be true. So it's probably because we are evaluating the model on the training set. So what does that mean? It means you are given a lecture, and then after the lecture there was a test. So if in the test I'm asking the same thing as what was given in the lecture, then that's not a very good evaluation of the students, right? In the test, what is being asked on the test has to be slightly different from what was exactly taught in the lecture. So how do we accomplish this test for the machine learning model? So when we are given a labeled data set, so this is our labeled data set, before starting out, we split it into a training set and then a validation set and a small test set. So the training set is used for optimization, stochastic gradient descent, fitting, all those kind of mechanisms. The validation set is used for picking the hyperparameters or the model class. So should you use a decision tree, or should you use linear regression, or should you use a neural network? So that's where you will pick the one which has the best performance on the validation set. And let's say you have done all the development and you are ready to launch your model or sort of conclude your project. Then you use a test set to report your performance or your model's performance, saying, okay, on the test set, the model performs 80% with 80% accuracy. So that's since the model has never seen the test set ever, this would we could take the test set performance as the performance of the model in the real world. Okay, so how do we do the test and train split? So given our X and Y, the complete data set, what we can do is we can use the scikit-learn library to split the data into a test set or a train set and a validation set by specifying the proportion of the validation set. So here it returns X train, X validation, X Y train, Y validation. If I run this, you see that we had some 1,700 examples, and now we have 1,500 and 270 in the two sets. So let's evaluate our logistic regression model. Let's train it on the training data, and let's evaluate it on the validation data. So we do the predictions on the validation data, and then compare the score, or compare the model outputs with the predictions. So once this finishes, now we will see that the accuracy is definitely not 100 or like 1. It would be less than 1. So you see it's 97%. So this is this is the accuracy on the validation side. There are other metrics, not just accuracy. So in some cases, the data sets are very unbalanced, or there is more data about one class of examples and less data about the others. So if you look at tumors and X-rays, there are more benign tumors than malignant ones. Or if you are doing fraud detection in credit card transactions, you have more like millions of more transactions that are legitimate compared to the fraud ones. So in those cases, the accuracy is not sufficient. And that's where precision and recall comes into play. So precision takes into account the false positive. So it's the true positives divided by the true positive plus false positive. So if your model is predicting false positives quite a lot, then its precision would be very low. And if it is doing a lot of false negatives, that is, it's missing out on tumors that are malignant, then its recall would be very low. So these two are used to excuse me. So precision and recall is used to evaluate when you have very unbalanced data. Now you might be thinking that, okay, I need low false positive and low false negatives, both are important. Then in that case, you can take the geometric mean of these two, precision and recall, and that's called F1 score. So just starting out as an introduction, these are enough. But keep in mind that these metrics exist. And of course, you don't have to code them up yourself. Scikit-learn have all these already built in, so you could let's do this for our model, the logistic regression model. So on validation set, it has a bunch of outputs. So F1 score for each of the class. So for class 0, class 1, up to class 9. So it seems like 0, 1, 2. It seems like F1 score for the word 2 or like the digit 2 is really high, but for others it's slightly lower. Okay, so that's that. Okay, so this was about metrics. There are a couple more slides. So question from the organizers, are we low on time? Do we take questions or go through the slides for now?
We're scheduled 12 more minutes.
So maybe I can quickly go through a few more slides and leave 5 minutes for the questions in the end. Okay, so feature engineering. So in so far we have looked at the models and how do we come up with the models, and we assume that X and Y are given. But feature engineering is about like how what the X should look like. What is the input? So feature engineering is the process of converting raw data into useful feature vectors. In the diabetes example, we already had these things, right? So imagine we had body mass index versus just height and weight, because height by itself is not an indication of any health, right? Or weight by itself, like you may be like 6 feet tall and your weight might be like very large, so it doesn't quite sort of. But BMI is useful because it does indicate some level of health, right? So those kind of things fall into feature engineering, where you want to select features that are more that have more correlation with the target. So if you have numerical inputs, then one hot if you have numerical inputs, then you can add it to the model directly. But what if you have categorical or labels as your input? So for example, like color, how do you represent color? So you could use a number for representing the colors. For example, like red equal to 1 and green equal to 2 and blue equal to 3. But in that case, you are embedding this prior to the model, or like implying that red and green are closer together and blue is further apart. Whereas red, green, blue doesn't have any sort of relationship, like 1, 2, 3 is not necessary. So that's where one-hot encoding comes into play. So when you have a red color, you say, my input, or like I will translate it into 100. And when it is green, I would say 010, and blue 001. So in this case, all of them are equally distinct, and this is called one-hot encoding. You also want to do some sort of normalization, and the most frequent one that is used is given here. So you basically do mean normalization or standardization, and what you do is you take the input x, you subtract the minimum of the column x for all the values that x has, and then you divide by the range of the values that x takes, so the maximum minus the minimum. Now this has the disadvantage, this kind of normalization has the disadvantage that what if your data has like most of your data is, let's say, between 5 and 10, but there is one value that's like minus 300 and another value that's like plus 300. So this kind of normalization will really squish your data between 0 and 1, but like very concentrated around 0.3 or something like that. So that's why standardization is used. So instead of min, you can use mean, and instead of this range, you could use the standard deviation, and that helps in speeding up the learning. This is some code doing the standardization, or what I just described on the previous slide. So you can run it and see what the effect of this is. Another common thing that you need to take into account is missing features. So in here, let's say we have features age, BMI, and blood pressure. And there could be cases where you have age available, you have blood pressure available in your data set, but for some inputs or for some examples, the BMI is missing. And that's the missing feature problem. So you could either drop this data, like this row from your data set, or you could replace this missing feature with the mean value, or learn another machine learning model to predict this BMI given these other features. So those are sort of like another area in feature engineering, which is missing features imputation. And another very important topic in introductory machine learning is underfitting and overfitting. So the gist of it that you need to remember is, if you have complex data and you apply, let's say, a linear model to it, then you are underfitting the data. And if you have simple linear data that could be explained by a linear regression, and you are applying a neural network to it, then you are overfitting the data. So that's both cases are not ideal, because when you come across the test set, when you do test set performance, so in the underfitting case and both in the overfitting case, you would have very poor performance on the validation and test set. So that's why you need to select a model that's the right fit, that fits the data the right amount. And the validation set basically helps you pick the model that has a good fit. Okay, so here is another tutorial on unsupervised learning that you could go through yourself. For useful resources, if you want to get started, I think this book is really good. It goes through a lot of other common machine learning algorithms. I enjoyed reading it, and I think it has the right amount of detail for someone starting out. And also Andrew Ng machine learning course on Coursera is a classic. A lot of people learn machine learning through this. So that's pretty much it from my end. Thank you for listening to me for the 2 hours, and yeah, I'm open to any questions.
Thank you for such an engaging.
So your audio is cutting out if you're speaking.
Okay, sorry, 1 second. I'm just gonna fix that. Okay, can you hear me better now?
Yeah, it's good now.
Perfect. I wanted to say thank you for taking the time to teach this very important lesson. There are a few questions I am going to quickly ask. Rishab is asking if we can say that in healthcare, if our priority is to increase recall values.
In healthcare, we need to increase recall values. That's the question. Like that's the
Yes.
so yeah. So in general, you don't want to have a false negative. So if you have cancer and if it is dangerous, then you don't want your ML algorithm to say, "Go home, you are good." Like that's a false negative, right? So that's why recall is sort of important. But at the same time, if you don't have if you don't need a CT scan and the ML model says like, okay, it looks to me that from the X-ray, it looks to me that it's a malignant tumor. Go do a CT scan. That's also bad, right? So depending on the problem, it's sometimes you need to sort of like weight the recall more than the precision. But at other times, if you are like doing some like invasive operation on the patient, then yeah. So sometimes you need to weight recall more versus precision, but you can't make generalized claims that in healthcare one is better than the other.
Thank you. I think that was all the questions left. If anyone wants to ask any questions, feel free to raise your hand. Okay. Oh yeah, there's one. Angelina has a question she'd like to ask. You're free to, yeah.
No, I just wanted to clarify about certain stuff. So you're just taking attendance and like we don't need to take any quizzes or tests to kind of like qualify for phase 3.
Yeah, if you already attended today, you don't need to take the quiz. So yeah, that's it.
Okay, but where is the quiz or how do I kind of like looks like for an attendance?
Oh, the quiz, we'll post more information on that on the Discord where it will be posted.
Okay, I see. Thank you. I will register
No
on
worries.
Discord.
Okay. Is there any more questions? All right. I guess we're good. And from the chat, everyone's saying thank you. I know I enjoyed the presentation. I'm sure everyone else did. So thank you again for taking the time to host this very important workshop. And yeah, I guess that will be the end of today's workshop. If someone's asking, I'm just gonna answer really quickly about review. It's recommended if you for next session if you review this material beforehand, but you can either go through the collab posted or watch it again, whatever you feel comfortable with. And feel free to ask any questions as you're reviewing on the Discord. So if that answered that, yeah, okay. All right. Thank you again, Dr. Khan, taking the time to do this. And I hope you all have a good night.
Thank you. Happy machine learning. Bye now.
Thank you. You too. Bye-bye. See you guys.